Hi, my name's John Kirkham, GitHub handle Kirkham. I'm here to talk to you about GPU packaging for the community. I think it's useful when thinking about packaging in the Python ecosystem to understand a little bit about our history and our users and our community generally to help inform the problem a bit. I've selected these two quotes here that I think are descriptive of Python and kind of inform how people got started with it. The first is from Guido. It says, Python is an experiment in how much freedom programmers need. Too much freedom and nobody can read another's code. Too little and expressiveness is endangered. The second is from Bruce Eckel, who writes a lot of books about intro to different programming languages. And he says, Python is executable pseudocode. And I think what both of these quotes capture is this general feeling that when coming to Python from another language, or maybe even for the first time, you feel like this language tries to be as simple as it can be without being simpler. It tries to keep things readable and succinct and understandable. It tries to give you a lot of power with a little bit of code. And so you can do a lot without making anything too complicated. And I think this is what really started to attract people to language in the beginning. And we see this in this XKCD comic here, right? Which I'm sure you're all familiar with. And so, in short, it felt like coming to Python, you had this real expressiveness and power with the syntax, and you could just do a lot really quickly, and you didn't get too bogged down in compilation or other things. And this is just as true about the scientific ecosystem. People were familiar with things like netlib and netlib's libraries, BLAS, LAPACK, and all of the different mathematical functions in there, special mathematical functions, I should say. And they were familiar with this, right? But they weren't necessarily rewriting netlib all the time. They were typically writing a little bit of code on top of these libraries, often in C or C++ or Fortran. And so what Python really offered is they could write this same code that they were otherwise writing in these one-time executables that would maybe get tossed. Just in Python, they could do it a lot faster and a lot quicker. They just write a little bit of Python code and they're ready to go, right? And so when people started seeing this, they thought, how can we take all the experience and knowledge and understanding of libraries like those in the netlib stack or things that mimic that API, and how can we expose them to Python so people can, have the power of these high-performance libraries in this high-level language with easy to understand and easy to read syntax. And so that's where SciPy was really born from. It was in many ways this first package that captured all of this functionality and exposed it to user in Python. And NumPy really provided this interface between these SciPy functions and, in general, just providing a way of working with arrays. And these were very powerful and expressive, and it really freed up developers to think a lot about what else they could then do. So they started building out the ecosystem, and more people started to come in and get involved. And they asked questions about, how can we plot data that we're looking at? Or how can we work with other types of data, like data frames? Or how can we do symbolic algebra? Or maybe, how can we more simply bind code together or even optimize our own code? in Python-like syntax, or maybe even other questions that weren't necessarily in those directions, but more about the interactive experience of writing in Python. How can we optimize it and make it faster? How can we allow the developer to make more choices at runtime? How can we improve that REPL feel? How can we create documents of exploratory analysis that can be shared between different people? Or even questions that, built on this entirety of the stack and thought about, how do we actually do machine learning or statistical modeling? How do we work with different data formats? How do we work with graphs? How do we do image processing? How do we do Bayesian workloads? How do we, and all of these questions kind of percolated up because of all this freedom and expressibility that Python gave people, and this core stack that got built out. And of course, I'm taking this slide from Jake Vanderplas's talk in 2016. And of course, he goes on to explore even more things that get added to the ecosystem until the screen is full of diverse variety of icons from all sorts of projects and problems that people are thinking about. But I think something really important started to happen here. The people that were working on NumPy or SciPy or Python, they were familiar with compilers. Compilers were really part of their day-to-day. They were writing in C or C++ or Fortran before. Maybe they did a little bit of Java as well. But they were used to this environment where maybe you have to compile and link things as part of your problem. And even, Matplotlib developers and other developers early on in the stack understood that concept of needing to build things. And some domain packages also use this for performance optimizations. But not everybody that was coming to the Python ecosystem, as it grew, necessarily knew how to use compilers or how to link libraries or how to handle these different problems. And so they'd report issues about different problems that they ran into trying to install packages and not really having the knowledge to debug, maybe not being even developers themselves, not even necessarily having that as CS class. And so with these different issues that were getting reported, developers then had to spend more and more time trying to debug these install issues. And the number of people coming and reporting compilation issues just was growing much faster than the development teams necessarily. I mean, it was growing at least as fast as the stack, and honestly, probably much faster. So there needed to be a new solution for distribution so that people wouldn't necessarily need to think about these compilation or linking issues. And so from this, the community thought about a bunch of different strategies that they could use. And there's a whole bunch of work in this area. I'm not going to talk about all of it. But I will talk about one particular piece, which I've had some involvement with, which is Conda. And what Anaconda provided by providing Anaconda was they provided this Anaconda distribution of pre-built binaries so that users could have this reliable experience of something that's already been built for them. They could even handle this as part of this packaging process. They could even handle compiler optimizations, like additional flags that might need to be added. They could handle special machine instructions based on architectures people are running on to just really eke out the best performance possible, which naively you might not get by just trying to build from source yourself if you don't necessarily know how to do those things. So it really baked a lot of knowledge and expertise into binaries and really enabled the community to move forward in a much more effective way to handle its growth. Um, and in particular, they didn't just supply a distribution, and like other people had been thinking about distributions too, but they supplied the Conda package manager. And so this really changed it a bit too. Because now you didn't just have a way of getting a pre-built distribution, but you could select different versions of packages, or if you wanted to start from a smaller install and only install some select components from their distribution, you could do that. And it also led into the next thing, which is they built Conda Build. And Conda Build gave developers the ability to make their own packages. So if something wasn't included in Anaconda, they could write a recipe for their package and explain the steps that were required to build it, and include that in this recipe, and then ask Conda Build, hey, can you take this recipe and go perform this build and generate a package for me? And then the result was a binary artifact that they could then share. And Anaconda provided anaconda.org, where you could take this package and upload it to your channel, and then you could maybe have a couple of things that maybe you share in your development group or your lab, or in a startup, or whatever your environment was. You could add this like small additional set of packages on top of Anaconda. And this worked pretty well for a while, but then some challenges emerged because people wanted to mix different channels with each other. Say, one development group might build packages that they're maintaining, another development group and another, department, government agency, what have you, might be building another set of packages, and they're interested in using them together, but they've maybe made different build choices along the way. So some of their dependencies conflict or don't work nicely. Or maybe they've decided that even some core things in the Anaconda distribution need to be built a little bit differently for their use case. Maybe there are some other compilation flags they need, or some features that aren't supported by default, or they needed to add another linkage to another library, some dependency that filled in some gaps in something they needed. And so there was this interest in changing somehow the set of recipes that Anaconda provided, and or recipes corresponding to the packages they provided. And Anaconda responded to this by initially having a repo of these recipes. And this grew for a little bit, but there's some challenges around testing and making sure that these recipes were staying up to date and continuing to work and not becoming stale. And really the amount of work there just ballooned. And at some point it just made more sense for the community to try to tackle this problem. And from that effort, Conda-Forge was born. And so this really supplied the way for the community to build and maintain packages all the way through the set of packages Anaconda maintained, ones beyond them. They could, extend the ecosystem to their heart's desire in whatever reaches and directions they thought appropriate. And so that's now been around for several years, and Conda-Forge is massive now with thousands of packages and similar numbers of contributors and maintainers. The numbers are always changing all the time. But that's really enabled the community to grow. So this then raises the question, what does any of this have to do with GPU packaging? Like, sure, I understand the story of why Python's interesting and why people built up SciPy and NumPy and Conda and Conda-Forge and these things, but how does this actually relate to the problem that we're trying to tackle? Well, the answer is it's actually exactly the same. There has been this GPU ecosystem that's been built out, and it's been built out over the years, and it's seen similar kind of situation where some core packages are built by Anaconda, and then maybe some are built by some other institutions. And so now there's this need to have this common stack yet again that all of these different community contributors can rely on to build and extend this ecosystem and make it easier for themselves and downstream users to use. And so here, I've obviously taken Jake's slide and tweaked it a little bit to throw in some of the GPU packages that people are using, but people are still also using the CPU packages from before. People are still using things like matplotlib and NumPy, and those still play a big role in this ecosystem. I mention this more not just to say that, like, here is even another set of packages that people are interested in getting and using. And there are other things that people from the community, like OpenMM, that's featured up here, or Goof, that are, interested in building their own packages and maybe a broader interest to the community. And so having that, community ecosystem for packaging really enables things to grow. So now that you kind of have a feel for why this problem is similar and why there are some challenges here, then the question is, how do we actually do this? So the first thing that came up was just trying to figure out what are standards that we want to have for GPU packages. How do we specify CUDA version? So, like, for those of you that are familiar with packaging, say on Linux, you might be dependent on a particular glibc version. And so this is tied pretty closely to your operating system and impacts what packages you can install and use and actually run on your system. There's a similar kind of story around CUDA versioning. It's a little bit more subtle because you really do want to use the latest CUDA version if possible, because there are always significant performance improvements being added all the time, and it's additionally tuned for more recent hardware. So if you have newer hardware, you really want the newest CUDA version to leverage the newer hardware. So you do care about keeping this pretty much up to date, but you can use the old versions too for a little while if it takes a little while to upgrade, or if you have older hardware, not too concerned about the performance improvements. And so there's this question of how do we handle this? You can read this discussion on Conda-Forge, but the short answer here is we use the CUDA toolkit package. So the CUDA toolkit package includes effectively what are the compiler runtime libraries for MVCC, which is the CUDA compiler. And we package those together. And so that is what we ship to users, and users can change what CUDA version they have based on changing this CUDA toolkit version. And there's some other things that have gone on here, like Conda is learning about how to detect the CUDA version the latest CUDA version that your GPU can support to help constrain the CUDA packages that get installed, so you don't get something that's too new that won't actually work on your hardware. Okay, so once we had like an idea of how that foundational level part was going to get solved, we then have the question of how are we actually going to facilitate these builds? Where are they going to happen? And so NVIDIA has done some work on building NVIDIA Docker and also Docker images with CUDA compilers in them. And so this seemed like a really natural place to start because Conda-Forge already uses Docker images for Linux builds. And so this is just a natural extension for the CUDA case. So we thought that we would use Docker images for the build, but we needed to make some additions to those images. And those additions were, adding mini Conda, adding Conda build, making sure the MVCC shim compilers in there, maybe even caching CUDA toolkit packages to like cut down on download times, this sort of thing. So we worked with the community on these images and got those added. This wasn't too difficult, and there's, it was mostly just an extension on existing images there to provide these features. The next challenge, once we had the images, was the MVCC, which is the CUDA compiler included in the images, is at the system level, whereas Conda is in this like user space kind of area, and so we needed to interface between them a little bit, and so we created this MVCC shim package. And so what this does is it provides a little bit of logic to figure out and link the right things when you're doing compilation, and it kind of tricks Conda build into thinking it actually lives within the context of that Conda environment. So Conda knows how to use it and compile, and there's like some additions there to make this work with the Conda compilers. And then finally, the last thing that it does is when you use a particular version of MVCC, we make sure that the CUDA toolkit package gets added automatically as a run dependency of whatever library that you're building, and that it gets constrained to match that CUDA version. So then when you build, let's say, like 10.2, you will get a package that is correctly constrained by CUDA toolkit version 10.2, or if it's 10.1, it's 10.1. And so then this ties back into this larger community discussion that we're having. So with this piece in, we now kind of have the building blocks. We have this Docker image. The Docker image has MVCC and has, the like extra CUDA bits we need. And we now have this MVCC shim for Conda build to do the builds. Now the real question is, can we actually tie these together in like a little experiment or a test run to see how to actually get this build to work? And so we picked a feedstock that we were like dog fooding ourselves and doing a bit of work on. That's like an early stage. And so we added GPU builds to this to just kind of test things out and see if that was working. And we got some feedback from people. We tweaked it a little bit, but more or less this showed that this approach had promise and could be used more broadly. And with a few changes, we could add this to the organization as a whole. And so that was the next thing that we did after we built those packages and tested them, was adding these bits into Conda-Forge more generally. And so now Conda-Forge has the logic with little tweaks to like the automated update tooling to basically detect if you're using the CUDA compiler to add the proper CI builds that you would need, to make sure those are getting built and make sure those are running on Azure, they're using the right Docker image with the right version, and all of that's getting tied together correctly. And now with those pieces in place, the next question that we really had is, can we use this on other feedstocks? Like if someone comes to us and they say, oh, I want to add CUDA builds to my feedstock, can we help them get started from there? And so here we engaged with the OpenMM developers who work on this open source molecular dynamics software, which is incredibly important in drug discovery and understanding genetic and other kinds of diseases, especially important at a time like this. And we worked with them to add CUDA support for their builds and help them get those into a test label so they could try them out before, sharing them more broadly with the community. And things seem to have worked out well. There was actually a fair bit of interest from others trying to get access to those packages afterwards. And this kind of proved to us that other people, like especially outside of NVIDIA, but even in the broader community as well, can pick this up pretty quickly with, a little bit of engagement, but nothing too complicated, and get something working. And so we've repeated this model on a few feedstocks, and now we've done several of those. And so now we're gaining a little bit of intuition about how to do these builds and how people want to use them and what kinds of things we might want to support. So now that we have done this work, I guess it's worth just summarizing like what we've actually been able to accomplish here. We've managed to add CUDA 9.2 and 10.0 through 10.2 support to Conda-Forge. So this is something that any feedstock is able to add. They make a few changes to their recipe, ask the automated tooling to come in and update their feedstock accordingly, and then it will add these builds and make sure those packages get built and uploaded as well. The packages are correctly constrained by CUDA version required, though there's ways to opt out if what you're doing is more flexible than that, and we've also explored that use case as well. For users that have packages that may have like a CPU only and then a GPU only case, then we want to supply both alongside, and so that users can choose between the two. And so we've actually been able to do this in a few cases and demonstrated this works. Of course, we've gotten builds to work remotely because all the builds are happening on Azure. But we can also do the builds locally and have engaged with a few people that are interested in doing local builds for testing and trying out packages to walk them through that process. And that's pretty straightforward and streamlined into how we already do local builds. So people have been able to pick that up pretty quickly with very minimal instruction. And I think this is a key point to stress here. There's no GPU actually required to perform any of these builds. And this is really important because if you're building on a machine that doesn't happen to have a GPU and then you're deploying to the cloud, or you're deploying to a local cluster, or maybe you have a beefy desktop that's dedicated for this work, and you can't, spend time building on that machine, you can do the builds on any other machine that you happen to have. As long as it's able to run Docker, you can perform that build. So that's really great for making it more accessible to people. And then, of course, it plays well with the Conda compilers, which was a little tricky initially, but works nicely well. And we've done a little bit of work also with the broader building community, like Kitware on CMake, to make sure that things work nicely with CMake as well. So that's what works well. The next thing to think about is what other steps we'd like to take as a community, like what can be improved here. Currently, we don't provide GPU testing on CI, so that would be a nice thing to fix. It would provide a bit more confidence about the packages that we're producing. Right now, we're effectively relying on upstream developers that tab releases to have done sufficient testing to make sure things work for us when we do the testing. There's like some tricks that you can do here to make sure that the testing suite does get shipped alongside your package. And we've done a bit of that to just make sure that we can like download the package and run the test suite locally. But it's still something that we'd like to improve. That said, when Conda-Forge started, we were heavily limited by build time. It was hard to debug builds. There were all sorts of issues that we started out early on with Conda-Forge at the very beginning of its history as well. And today, many of these issues are alleviated, if not completely resolved. So I'm hopeful that we'll be able to solve this problem in the future when working with the community. It's just something that we need to keep in mind and keep an eye towards how we can improve in the future. The second thing is, while we've gotten this to work with feedstocks, and it is technically possible to do builds and stage recipes, there's no real baked in support to stage recipes. So if you're adding a new package to Conda-Forge and you want to add GPU support, we don't really test that build by default. Now there's ways to get that test to work with a little bit of tweaking, and if you're confused by that, we can certainly point you to examples on how to get it done, and it's not complicated. People have managed to do this successfully. But still, it's a little bit of friction that would be nice to alleviate. So that's something that would be nice to improve. And I think a key point here is in stage recipes, normally the process now, how it works is we build all architectures in all cases, regardless of whether regardless of whether you support them or need them. And so if you have some recipe that you submitted, we'll do Mac builds, we'll do Linux builds, we'll do Windows builds, we'll do ARC builds, we'll do PowerPC builds. And if you're only supporting Windows or Mac or Linux and Mac or some combination like this, we're wasting a couple builds, but it's not huge overall. And more often than not, people are trying to support all of the architectures and OSs they can. So in general, the waste there is minimal. With GPU packaging, it's a little different because you're writing usually specialized code to take advantage of GPUs. And so not every package is going to do that, or even if they do have GPU bits, maybe they rely on lower level libraries to really have those GPU bits and then do something like choose between NumPy or CuPy or something like this at a higher level. And so in those cases, we don't really need to be building GPU packages. And so we need a little bit of this selection logic to make sure that, we only do the GPU builds on stage recipes for recipes that really need them, as opposed to just doing them across the board, just to conserve resources and be thoughtful of others' needs. And then the last thing is now that we've gotten a few packages and we've developed a little bit of expertise, we've seen different ways people want to name packages, and then of course there's some naming differences between different channels, and so there's some interest here in figuring out how we can standardize things a little bit. And so this is not an impossible problem to solve, but we just need to discuss with the broader community and see how people are using these and see how naming needs to be transformed to reflect how people use things and what works well. So, and this isn't a comprehensive list. There may be other things that we determine as we go forward that need improvement, but those are just a few of the things. What I'd also like to add is we do have some upcoming work as well. In particular, we're working to add CUDA 11 support as well. CUDA 11 is a little trickier than the other CUDA versions that we've added thus far because CUDA 11 meant dropping CentOS 6. So it now requires CentOS 7 as a minimum. So we need to do a little bit more work to move to CentOS 7 for those builds. But it's not impossible, and there's already a need to move to CentOS 7 as CentOS 6 approaches its end of life. And this ties in nicely with other community work to add CentOS 7 support in Conda-Forge. So we're just getting started on that now and figuring out things out. We're certainly happy to have other people from the community hop in and help contribute to the effort. So if that's something that's interesting to you, please reach out to us and we can help direct you. The other thing that we're looking into is adding other architectures. So right now we have builds with x86-64, but there are people who are using PowerPC, and we already have PowerPC builds in Conda-Forge for CPU packages. And so there's a need to solve that problem and make sure that there are CUDA-enabled packages built for that architecture so people can get access to those more easily. The other one that we're looking at is ARM. ARM's become a very exciting architecture in recent years. People have explored it in hobby devices or sort of like edge computing use cases for like inference and other things. Like NVIDIA, of course, is exploring this and others are exploring it as well. Obviously, Apple announced that they're moving to a ARM-based chip. There's also some work to start adding ARM-based clusters to take advantage of the lower power usage. So we're interested in building out that ecosystem as well. And again, much like with PowerPC, there is ARM support for CPU-only packages in Conda-Forge. So then this is more a question of like, can we do this with GPU packages as well? And so that's something that we're like looking into and pushing on. And we certainly, welcome community engagement on this too, on all of these efforts. So normally at this point, I would ask if there are questions, but in a recorded talk, it's a little weird to ask for questions. So I guess what I'll say is please feel free to reach out to us on GitHub. Again, my GitHub handle is Kirkham. You can drop by like with an issue on Conda-Forge if there are particular things you're wanting to build GPU packages for and you need help or guidance with, we're happy to direct you. Also, feel free to stop by in the Gitter chat, the Conda-Forge Gitter chat. It's pretty active there all the time. So we're happy to talk to you about issues you might be running into, ideas that you might have, things that you'd like to help with or you need some support with. So yeah, please reach out. And with that, thank you for your time. Please stay safe, stay healthy, and I look forward to seeing you soon after we leave the lockdown.